So now we're going to be moving on to part one of part B for exam 3. And the scenario that we have here is we have a cooling tower situation here. And what this is right here, this is the packing material for that. And what we have, the way that a cooling tower works is we have liquid that is flowing down. This is hot liquid that is flowing down the cooling tower. But we have a cool gas flowing up through there. And what that gas is doing is it's cooling down the liquid. So as you can see here, it starts out hot, but down here it gets colder, or cools off at least. The packing material, we have that as the area of A, and that is in meters squared over meters cubed. There's also like a cross-sectional area there. And essentially, we're also going to be looking at the distance. Now, we know that distance we're going to be measuring with Z, and the distance at this top part right here where that packing material is going to be considered 0, but the positive direction is going to be downwards. So Z positive is going to be headed downwards. And the last thing we need to know is that there is going to be a mole fraction of water that is going to be going through, because there's going to be a lot of water vapor going around. There is a liquid here, there's gas here, there's water vapor going around mixing between. Now, another thing we need to note is that we have a gas flow rate here, and the gas flow rate is going to be the sum of that gas flow rate of the air and the gas flow rate of the water vapor in this sense. Another thing that we're going to be looking at is that right over here, we're going to be needing to find these differential equations, and yeah, we're going to be focusing on solving it. That is what we were trying to figure out in part one of part B. So we're going to be trying to tackle this separately. We're going to have these in separate parts. We're going to have part one be the change in that mole fraction to the distance. Part two is going to be change of the temperature of the water compared to that distance. In part three, we're going to have as that change in that the temperature of the gas over that distance. So we're going to start off with part one right now. And the way to solve part one right here is we're actually going to be needing a mass balance here. Mass balance. I'm writing these out so that you can see where I'm working with here. And the equation we're going to be needing to work with here, since we're having that mole fraction over the distance, we're going to start off by having that cross-sectional area there. That's the bad part about writing with the pen. And we're going to have that to that change in the gas flow rate over the molecular weight times that mole fraction, and we're going to have that equal to negative of that mass concentration or mass transfer coefficient of water. We need that to be part of the difference of the concentration from the surface we're talking about up here to the concentration away from it. We're also going to multiply that by that area that we have up here, the area that we have for that material. And again, we're also going to multiply that by that cross-sectional area as well. And we're going to finish it off by having it be relative to the distance. Now, from here, what we really need to do is just break things down a bit. So obviously, we can get rid of this cross-sectional area. That's going to be a common theme here, but we're still going to write it down because we need to know what is there. I'm going to keep writing it, but on every equation, I can already tell you they're going to be gone. Now, past that, we also need to, we're essentially, again, we're looking for that comparison of the difference in that mole fraction compared to the distance. The issue right here is we have this gas flow rate over that molecular weight, but those are actually going to be constant throughout the entire thing. And therefore, since it's constant, we actually can pull that out. There's no reason for it to be in there. So we're going to actually rewrite that as this outside of it. And if you're already seeing it, that's great. If not, don't worry, keep following. I just realized you weren't seeing the bottom part here. Essentially what I did was I took these two, divided, rewrote it out here as you can see, and we moved that gas flow rate over the molecular weight to the right side here. And then what we're doing on top of that is that we're taking that molar flux and we can actually change it to be the mass transfer coefficient multiplied by that change in the concentrations from the surface to away from the surface. And that'll just allow us to substitute this in here, which allows us to kind of just shorten this up a little bit, make it a little bit smaller. So we're going to rewrite this. Now you can see it for sure. As G. I'm just writing this at the side because it's just for you to see. We took that, oh, there should be a negative there. We took this part and this and just moved it over to the side just so that you could see how it works there. And that gives us our first differential equation of the change in the molar fraction over the distance z. Now for the second differential equation, right here we have it as the change in the temperature of the water relative to the distance z. I'm going to first quickly explain, again, how the temperature works. So essentially, again, how temperature works here is there's a liquid on this side and there's a gas on this side. And what that liquid is doing is it's hot on this end, and as it travels down, that gas helps cool it off. And it gets to a cooler temperature down here. But the gas, though, it's getting heated up from cooling off. The liquid, it's got to go somewhere, so it gets hotter up here. Now, because of this, we're going to actually be working with energy balances. So in this one, we're working with energy balance. I'm going to try to keep an eye this time to make sure I don't stray off and write it on the other half of the paper. And the equation we're going to be using for this is going to be, again, we're using that cross-sectional area. Don't worry about it, but it's going to be there for now. And we're multiplying it by that liquid flow rate. That liquid flow rate of the water going down times the heat capacity of that liquid, and we're multiplying that by that change in the temperature of the water. Again, I'm not going to be turning it around. And we're going to set that equal to essentially we're going to have that equal to the convective heat transfer. It's going to be from the air to the water here. And we're going to have, again, that multiplied by that cross-sectional area. It's got to be there. And we're going to have that be multiplied by the difference of the temperature from gas to water. And we're also going to take that and subtract it by the heat of vaporization times the now known value, well, not known value, but we know that the molar flux, we kind of figured it out how it worked in the last question, times, again, that cross-sectional area, but then we also multiply it by the area that we have there before, multiplied by dz. And so from here, it's actually not that hard really to cut this off because we don't have to worry about these two values. We're trying to find that change in the temperature of the water relative to the distance z, and because they're already separate, we don't need to do any tricks to try to separate them, make them different. We can just go ahead and do it right now, actually. We can take it all off. We're going to start off by still cleaning this up a little bit. We're going to remove those cross-sectional areas. We don't want those around. And then after that, what we really just need to do is we need to take these values and just subtract it over to that side. It's going to end up being written as that change in the temperature of the water over that change in distance is equal to that area over the liquid flow rate times that the capacity of the liquid. We're going to have all that multiplied, it's all going to be working together, by that convective heat transfer of the air and water, times that change in temperature, minus that heat, not heat capacity, sorry, heat of vaporization, times that molar flux. And that actually gives us our second differential equation. Another thing to add that I didn't add here too was we're also going to have that equal to the difference in the enthalpy of the water. And this is going to be important for part 3. So for the third differential equation, we're actually also going to be sticking to energy balances. And it's going to work kind of similarly to how we worked with the temperatures, but it's not going to be exact there. We're going to be working with enthalpy here, though. That is why on the last problem, the last part, I was showing how that equation, I can pull it up right here, this equation is equal to that change in enthalpy of the water. An important thing to note here is that we're working with a steady state process. So because it's a steady state process, we know that that change in the enthalpy of the water, enthalpy of the gas, has to equal 0. And because of that, we can simplify this down that we know that these two values must be equal to each other. That's very great for us to note because we actually already have that change in enthalpy of the water we figured out in the last problem, so we're going to be working with that here. Now, to start us off with this equation, we're going to have D, and again, we're going to have that cross-sectional area. I know it's there. We're going to have that gas flow rate there too. We're going to have the heat capacity, but this time we're doing the heat capacity of the gas. We're going to have the temperature of the gas here too. This is going to be added to that heat of vaporization, which is going to be fully multiplied by that gas flow rate, the molar fraction, again that cross-sectional area, and the molecular weight. And this is all close together. I kind of didn't leave a lot of room actually here. I did not leave a lot of room actually. I'm going to rewrite this quickly. Okay, so we're going to have that equal to that area that we've been talking about. And again, we're going to have that cross-sectional area. It's got to be there. I don't have any hate for it. I'm just making fun of it. We're going to have that heat there. And we're going to have the change in the temperatures. And we're going to have that change in the temperature from that gas to that water. Ooh, that was poorly written. And then we're going to have that also again subtracted, and you'll see maybe a pattern. I'm hoping that you're going to be seeing it here. That heat of vaporization times the molar flux times that area times that cross-sectional area times finally we have that dz there. I'm going to go ahead and start cutting things off because this is a big jumbo mess here. Of course, we want to get rid of that cross-sectional area. We always want to get rid of that. Everywhere you see a we don't always. I'm not going to make that claim right now. But where you see a cross-sectional area in general, you're going to be crossing it off here. And also what we can tell from this is that the gas flow rate and heat capacity are constant right over here, what we have here. So we can actually take those and pull it out, which is really, really helpful for us because that does not leave us with a lot, because we can now take that gas flow rate times the heat capacity of the gas. All that we're really left with here after we take that out is that change in the temperature of the gas the change in the temperature of the gas. We're also going to take that dz there, and we're just going to go ahead and divide it there too, so that we get that change in the temperature of gas over the change in over the distance. And so we're also going to go ahead and have this added again like it was before. But here we're also going to have, because this was that d to the Tg and that change in the temperature of gas, and also on this side, because it's added the change, we're going to have as the change in the molar fraction of, the change in the molar fraction. So what we're left with is we're going to be left with that constant here, but we're left again with that molar fraction, but because we've divided by that dz, we have dz here. And on the right side, it's going to be generally the same, other than we're removing some things from there. G minus W. And also another thing to note here while I'm writing is that we already have this value from part 1, which is very helpful for us. And because of that, we can't have this here right now. We can't call this problem essentially solved. We can't just move everything over one side. We need to include this. Now if we pull back up the first part, we remember that that value was negative the molecular weight times that area over that gas flow rate times the molar flux. See, it was really helpful to change that to the molar flux because it's a lot easier to see. So I'm going to go ahead and just rewrite that down. So we're going to rewrite this, but we're going to have now that change in the mole fraction. We're going to rewrite it to what we found out in the first part of this question. So we're going to have, again, G, C, G, and that change in that temperature, gas, Z, plus that constant there. And we're going to have that multiplied by, again, what we had there was we had that it was the negative the molecular weight times that area over the gas flow rate times that molar flux there. This is actually really nice because since it's being multiplied by this, we can go ahead and cut those off right there. We're keeping that negative though. That negative can really be moved up there, but we're leaving it there for now. And what this helps us see is actually that we can now begin to see similarities on both sides. If you don't see it already, I'm going to continue drawing it out for us. So what we can see here is that, let me rewrite it actually again because it kind of looks a little weird. Or I'm writing that as a minus now. And I'm rearranging this because we're now going to see these two are the same. Because there's an equal sign there, they're both negatives, we can go ahead and cross them off. They're just going to be added to each other. They're the same thing. And this brings us to our conclusion, where now we can just divide by this, and that's a weird looking G, by that G and that gas flow rate and that heat capacity of the gas, we now can find, I made a G there, that the difference in the temperature of the gas relative to that distance is equal to that area of H over that gas flow rate times the heat capacity of the gas, and that is all multiplied by that difference of the temperature of the gas and the temperature of the water. This gives us our third equation.